Hello, everyone. In this video, I would like to explain why I think that the C++ metaprogramming is actually terrible. So the title of the presentation is a bit joking that C++ metaprogramming sucks and is not getting better. So who am I? My name is Andrea Griffini, and I've been professional programming for about more than 40 years now in many different fields. I started with accounting, then I moved to medical imaging, then video games. I wrote just one package for an off-the-shelf software for young people. Was a painting program. I actually worked on two of them, and back in the 80s. And lately, I've been working mostly on robotics and more specifically in artificial vision and also in an optimization problem that is called the nesting problem, where you are trying to save material by optimizing the position of various parts you want to cut on some sheet of material, sheet of leather or whatever. And as a paid worker, I mostly work now in C++, but this C++ is also my language when I do my experiments with my toy projects, side projects. And I've been actually using C++ 11 right now. And at work for historical reason, we have some backward compatibility problem with some development environments that are not easily upgraded, and also because I think the C++11 and maybe C++14 that fixed some bugs is the best C++ I can think to. A newer version I've been following not very closely. I have to admit, I don't read all the specs, I don't try all the stuff, but I've been following the evolution, and I don't find anything that is that interesting for me in newer versions. More on this later. And I've been following the C++ evolution of the language since the beginning. I mean, since before there was a standard C++. I've been working on early compilers. The first one I remember was using the Borland C++ compiler. Then I used, of course, GCC and Microsoft Visual C compiler, and with the C++ compiler. And so when I'm talking about metaprogramming in specific, I will start from the history of metaprogramming in C++. And so I will also cover the evolution that we got into. But please remember, when I say something, I'm referring maybe to how it started. Like I said, I'm using C++11, and because I think that's a huge advance in respect to C++ 0303, that was the previous versions. And more specifically, I find that the ability to use template in local functions, the local structures in templates in local function, and the Lambda implementation are game changers for how you write code in C++. So when I write in code in C++, I really use those features that are only C++11. And also thread support is important, portable thread support. Much of the rest is instead, let's say, so-so. So I don't care much about the other stuff that new versions got. So, first of all, what is metaprogramming? And please remember, this is my definition of metaprogramming. You can define the word whatever you want, but for me, it's code that manipulates code. And with this, it means that a metaprogramming function is just a regular function in which either the input or the output is actually code. So at least one of the two or both of them. And This definition means that, for example, you can have a function that accepts just a number and generates code that makes something for this number. For example, compiles some functions, returns to you a function that, given that number, computes solves a linear system, for example, or a couple of numbers and does that, or can be just a very simple function. Of course, the most easy metaprogramming function is just returning some code without any kind of input. That's kind of what's normally a macro, just a defined macro is. One important thing is to understand is that to manipulate code, you need a way to represent the code as data. So the meta function can actually access this code if he has to do any kind of analysis. And the result of the meta program must be also is data, but must be interpreted as code. So we need a way to represent code as data and to interpret the data as code for the output. And this is one way in which you can read the code is data, data is code mantra. There are many different dimensions to this. You can go deeper, but this is not for this talk. So we are caring about very specific problems, but it's important to understand that this kind of representation is a necessity if you have to write metacode, because you need to do some manipulation. This kind of necessity is really just really simple to solve, to provide, if all you do is just code generation. So you don't need to do any kind of analysis of code, any kind of introspection. Then just for generation, it's almost a non-problem. So let's see a few metacode examples. First, remind us that since metacode is just code, this is not an exhaustive list of possible problems you want to solve, because that would be like creating a list of all possible programs and doesn't make any sense at all. The first is code generation. Like I said, your input may be number, or maybe just code, but there is no analysis. That code is just, for example, used for substitution. So you have your meta function could be, for example, a sort of a template, a predefined code in which some part must be substituted from code with code provided by the user. So it's just slightly more complex than a quoting problem, that where you just return a fixed piece of code. And this is in metaprogramming parlance is normally referred to as quasi-quoting. That is quoting with the variable substitution. And this is the simplest case of a metaprogram. Oh, the simplest is just quoted code. This is the second simplest possible problem you wanna get. Generation can also instead be more complex. For example, there could be an algorithm doing some stuff. Another opposite problem is when your metacode just does analysis. So the output is not, maybe it's just a number, or maybe there is no output at all, but only side effects. And your code needs to analyze some code provided by the caller. And for example, the code provided could be just a structural definition. You want to extract the member names and create an HTML file, or an XML file describing the members of your trust. So this is code analysis, introspection, and this requires a way to represent the code and to analyze this code. And a mix of the two is just another example, is a kind of a modification. So I get some code from the user, and I need to inspect, change something, and return a modified version. So it's very different from code generation, because there is no template. I'm getting the code from the user, and I have to find where are the substitution I want to do. And okay, those are just 3 examples. So how can we represent the code? Well, the simplest way is just a stream of characters or a string. And this is very easy for code generation. But if you need to do any kind of analysis, things are very complex because you need to implement a parser for that. And that can be not trivial, especially in a language like C++. Then there is another possibility that is using tokens. And if I'm not mistaken, this is what Rust, one way of writing metacode in Rust works. So you get a stream of token as input and you produce a stream of token as output. It's also how the C preprocessor works. And this is also makes things reasonably easy for generation. It's really difficult for analysis for the very same reason, because it's just the same, just at a slightly higher level. And then we have code and abstract syntax tree. That's another kind of representation. If I'm not mistaken, this is how the other way of writing metaprograms in Rust works. And this is much better for analysis, but the code can look alien. What do I mean with this? This is, for example, the AST representation of the statement x equal x plus 1, where x is a local variable, a parameter. And this is the AST produced by clang and compiler. And as we see, we have a binary operator node at top level with a reference on the left side, a binary operator on the right. But the left side of this second binary operator is an implicit cast, and there is a reference there. And then we have the literal one. So I made a little drawing for this. The statement x equal x plus 1 generates this kind of AST on clang. And so the very same x in the source code, I don't see any difference between the left x and the right x. They look the same. But this generates different AST representations because of the rules of the language. So even if the representation is the same, that's possible. You just moving down later in the analysis this kind of implicit promotion. Still, there is the look on the left side, the look to the right side is not exactly the same. This can be a big problem or cannot be a problem, depends, but it's a problem. Can be a small problem, but in my opinion, still makes your metacode looks weird because it's not acting on the same thing that you were writing. I mean, you were writing x plus 1, and this is working on something else where there are precedence rules or whatever, so the structure is not obvious. Okay, so what does C++ provides, or actually provided when C++ was designed? We get code generation by template substitution that, as we saw before, is also named quasi-quoting. Except that's a bad implementation of quasi-quoting, and I will explain why I think that this is the case. And nothing else. Really, this was all of it. And no way to do any kind of analysis, no way to do any kind of transformation, just code generation, and also not code generation in general sense. So you cannot write complex code generating a code result. You can just a template with substitution, nothing else, and no computation at all. This was the design, was the idea of the template. And also this quasi-quoting idea, even just consider it to be quasi-quoting without not attempt to do anything more sophisticated, was also a bad implementation. And why I'm saying so? C++ template substitution, in my opinion, has a few structural problems that are not easy to solve. And the first is that substitution points are not clearly marked. So when you see a template in C++, the substitution point are just identifiers, just the name of the parameter. And that's all. There is no clear marking at the grammar level. So if we consider, for example, the template strings in JavaScript, that is the backquote string, you have a clear marking that is $ open brace. That is where the substitution happens. This works inside a string, so it's a little bit different. But if we consider, for example, what is, in my opinion, one of the best implementation of the metaprogramming tooling, that is Lisp, Common Lisp, and Lisp in general, but Common Lisp as a practical implementation of this idea, you get quasi-quoting, but the substitution points are clearly marked. There is a comma operator that is used just for that feature. So if you look for commas, you know that you are inside that template, and that's the substitution point. And then you have the comma splice for inserting a list, splicing in a list. I'm not getting into details, but just looking at the template, even if you look at the middle of the template, it's clear where the substitution points are. Instead, the C++ is just the identifier, with also some weird rule, like you normally in C++ have hiding. So if you open up a block and say int x, I declare an integer variable x, this x may shadow something that is on the outside, but you cannot shadow a template parameter. And why? Because there is a rule that say you cannot. So you get a compile error for this reason. And this means that is when you look at the code, it's even not obvious that when you modify a template, you must pay attention. Even if you're just changing the core of the algorithm, you must be sure that the names you are used are not template parameters. Normally, template implementers use tricks like adding underscore everywhere, including in parts that are forbidden for any user code. Just to try to solve this problem. Another big problem, structural problem of template substitution, is that the template it must be a complete entity for the C++ compiler. So it must be a complete structure or a complete function. So you cannot have a template for just a little part of what you are trying to implement. And this is quite annoying because sometimes when you want to write a code generator, you have some different parts you want, and that would be helpful to have just a template for those parts, you quasi-plotting for those parts, and but this is not possible. In C++, template substitution was at the full structure level, and that's it. And there is no way to do partial templates. And also, this was not seen as a big problem in the beginning at design time, because there was no way to make anything fancy. So you do not add any kind of computing power on no language to do anything except just substituting parameters. And so this was not a problem. But later, when the language had evolved, it was discovered to be possible to do some computation, this kind of structural requirement that the template is the full thing is annoying, and really creates problems when you write code. You needed to create temporary classes just to do something, because the temporary classes is the minimum unit you can use for a template. And another big point is that substitution value cannot be an expression, like in JavaScript or Common Lisp. When I replace $, open brace, I can put any expression there, and so I can compute the stuff I want to place it there. In C++ templates, this is just the template parameter. There is no possibility to do anything else. And this is also because there is no way to mark the expression. You need some way of syntactically make clear what should be computed at compile time and what should be the result instead part of the template. So that's why I think that the template substitution is only quasi-plotting. So it's not the most trivial, but the second most trivial problem you may want to solve, also implemented badly. And then we got the compile time computation. This is a very funny story, because that any non-trivial computation was actually possible is something that was discovered was not designed, was not thought about in advance. It just happened to be possible because of three different hacks and the way they interact. First, there was overload, and more specifically, overload the resolution rules. Overload is this feature of C++, which you can have the same function that can have different meanings depending on the number and the type of parameters. And the rule for resolving this ambiguity are quite complex. I'm pretty sure that if I ask even an expert C++ programmer to write down the rules, he won't get the rules right, all of them. And still, you can use, if you don't do anything too fancy, maybe you get some slap in the face when you make a mistake because of that. But you don't normally want to do anything fancy with the overload resolution. After all, having the same name for different things is not something that really helps a lot, excluding very simple cases. And one rule that was, however, kind of simple was that any variadic function with variadic with the meaning of C variadic, so like printf, so the three dots in printf, any variadic function was the last to be considered. So when there are multiple options, if there is a variadic one, that's the last one to be taken into consideration. And this was used as a trick by adding the template you wanted to be resolved as last option with a variadic definition that where actually there was no parameter there. It was just to be sure that this was the last one. This was the first trick. The second trick is even weirder, and it's called the SPINAE. And it's an acronym for substitution failure is not an error. And the meaning is that if you have a compiled error of a certain kind, not all kinds of errors, just there is a quite strict delimited subset of errors that you can get. If you get this error in a specific point of a template declaration, so it must be in the signature of the template, not in the body of the template, not during the substitution, and then that's not really an error. So the compiler should just ignore that template and remove that template from the list of overloading resolution set, from the overloading resolution set. So that template should be ignored. And that's kind of weird if you ask me, but this is how it worked. And the third is recursion. And with recursion, I don't mean the composition ability. For example, if you have a std vector template, you can have an std vector of integers. But that doesn't mean that the std vector is recursive. Simply means that std vector can accept another std vector as a plugged in for substitution. So the second call to the vector template is made by the user that is calling installation. It's not part of the body of the expansion of the vector. But there was nothing that was forbidding recursion in the definition template, so you were allowed to use recursion. However, having recursion without having a way to do a base case would be pointless because you would only get infinite recursion, so exploding templates. But thanks to the other two tricks, you were able to create certain kind of errors. The most common used was an array with negative size. So you were able to create this kind of array in the proper point of a template to exclude the template. The overloading was choosing another template, and this was the base case for the recursion, so your recursive function was able to complete. And those three basically allowed the template substitution to be Turing complete. Let me repeat, this was not intentional. This was discovered later. And this would have been funny, because Turing complete means that you can perform any kind of computation, and this would have been completely okay if there was another important point that the fact that this is Turing complete, so you can do any kind of mathematical computation with it, doesn't mean you should do because there are many languages that are Turing complete. One example, a notable example, is brainfuck language. That is a very simple language, just 8 characters define the whole thing. And it's Turing complete, but doesn't mean we have to write code in brainfuck. Absolutely not. It's a audible language to write code in. Doesn't make any kind of sense to write any real code in. Can be a funny exercise. It's a nice party trick, but it doesn't make any sense at all. And in my opinion, the same applies to template metaprogramming in C++. So Bennington Incomplete, in my opinion, this discovery made a huge damage to C++ metaprogramming. Why? Because for quite a long time, the decision was that if something was technically possible to do with the templates and substitutions, and that's recursions, finite, and all that kind of bad trickery, then should have been done that way. That was the solution. And if something was really, really impossible to do, then a little bit was added to the template machinery so that something became possible. In my opinion, having a way, a terrible way, almost unusable, was the code, because the language is so weak, the code is absurdly complex. It's difficult for the users, it's difficult for the compilers. For quite a long time, it was very common to get internal compile errors when using templates. It's impossible to debug. Still today, if you want to see what is happening at compile time during template expansion, you cannot do that. There is just, you get the only way is to run the compilation and see what happens. And the error message are literally a joke. There is even a competition about getting the longest error message from the smallest source code. So basically, your score in the competition is the ratio between the error message length over the source code length. And we are in the billions. So you can produce errors of gigabytes of length, gigabyte of errors from a very small source code. And this is nonsense. I remember a company that was making money just by selling a single product that was a plugin that was able to decrypt the error message and tell you, for example, you are passing a const reference and instead the function doesn't want a const reference because it needs to mutate the argument. And so this kind of translation between 10 screens of bubbling nonsense in which there were a lot of things that didn't make any sense at all because of what the sample was talking about, error in temporary classes needed just to be able to do what the code was trying to do. Instead of getting that kind of crap, you could get an error message. Oh, I'm passing a const reference, but this is not correct because the call will mutate my object. And making a business out of that. So that's the situation. I don't know how better it is now because then still the error messages are quite terrible. Maybe they are not as terrible as in the past, but the problem is the real issue is that having a way, no matter how bad it was, for every possible dimension you want to look at it, was technically possible, then that was the way. There was even a library, a huge library of complex algorithms that named Boost, implemented in templates with different workarounds for the different compilers to avoid internal errors or big limitations. And part of Boost was even taken inside the standard library. And so this is, in my opinion, what prevented us to get any kind of reasonable metaprogramming language for more than 20 years. Right now they are adding every 3 years something is added, but the main desire remains. The way to metaprogramming is template substitution. That is bad quasi-quoting implementation. You got const-text. That's a really funny thing on itself. But I think still we are still there. So what are the big issues, in my opinion? Metacode is essentially complex because code object the code is complex, is hierarchical, recursive in nature, can have a general topology graph as a structure because references between types and functions and whatever can be really complex. So of course there is some implicit complexity. Any code, any metacode tends to be on average more complex than regular code that works on simpler data structure like an array of numbers. But in C++, most of this complexity is just artificial because of the limitation of the language, not because of the problem you are trying to solve is complex. And so this is a big issue. The other issue is that the syntax should be simple and uniform because in metaprogramming you need to analyze the syntax in the general case. If you're generating that trivial case, that doesn't matter. But if you do need to do any form of analysis, the simpler is the syntax, the more uniform is, the better it is. This is also very important because if you have, let's say, 10 special cases in the syntax, 10 special forms with structure, your metacode needs to handle all 10 of them if you want to do analysis, because this is what the code provided by the user could contain. So you must have the knowledge of those 10 forms. And if you decide in the future to add a new one, the problem is that all the metacode you wrote in the past is broken now, because it can get a parameter that is code, the code can contain the new stuff, and so that meta function will not know how to handle that. And so this is the third point. In my opinion, static typing doesn't work well with metacode for this reason, because your metacode must be able to manipulate nodes that doesn't know in the detail. Maybe it doesn't know the semantics, but must still know how to navigate them. So you need to have some kind of runtime at compile time. This is more this on next point. Dynamic understanding. This is something I found myself when writing my own compilers. Programming languages are one of my passions, so I wrote many compilers. A few of them ended up in production, but something that I found about metaprogramming is that static typing doesn't work well with metacode because complicates things a lot. I'm not saying it's impossible, but really makes things more complex for no gain at all. And this is something that was also recognized by the standard committee, because the last proposal for introspection uses this kind of dynamically typed code object for representing code. But this is kind of against the grain of C++, And another point is that there is this obsession about compile time and runtime separation. When you allow user code to be executed at compile time, it means that compile time is runtime, and you should have all the language at your disposal. If you want this cues for separation and why the compile time language has so many limitations is officially because you want the compilation to be without any undefined behavior and always working. But it doesn't make any sense. Once you allow Turing complete code to be written by code written a Turing complete language by the user to be executed compile time, you must face something like there is no guarantee that the program will even terminate. Let alone that's correct. Just even terminating is impossible to know beforehand. This was proven many years ago, before the computers were invented. So it's not something we have an idea of. We know that this is the case. It's impossible to get guarantees about the code if the code is still incomplete. So either you have two choices. Either your language is too dumb to be interesting and too powerful to do any kind of computation like Turing complete, or you must face that maybe the compile time code will be broken. But this is not your problem, it's a user problem. So I don't see this excuse holding any kind of water, in my opinion. And it's just a bad idea to put such a limitation. Yet it's something that is really, really fixed in the mind of the people of the committee. Not sure about the general users of the C++ language, but that's another sad story. Is that the standardization over the year changed the meanings. In the past, was we found what works well in the field, it gets standardized, so we all agree. After we found that something was well. Now, instead, the standardization is just there is a bunch of people, a few ones, mostly who wants to be in that group, and those decisions are applied without discussion on all the others, because they are the thinkers, the others are just the doers, and they have to accept whatever comes from this elite of good thinkers instead of what is emerging as a good idea. And this completeness session is very, very strong in that elite. And I don't see. I think this is a very stupid take. There is no reason for that, and there are no excuses for that. But this is what the language is, because the way it works. And another big issue is that when talking about the metaprogramming in C++, basically it's only about structures, and at most these member signatures. That's the only extra thing that you may get to. But no one is talking about, for example, the body of the methods. So if I wanna metacode, interesting cases of metacode are the ones that are dealing with the body. So finding if your code is doing something and maybe replacing some part of this with something else. So this is really a big limitation, as this is something that is not even on the radar. It's really beyond any kind of thinking for that elite. So they think that the metaprogramming is just about the structures. And this is funny, because even about the structure, we are still, maybe we will get in C++ 26. I think the proposal was accepted, so we'll be in C++ 26 after, I would say, 30 years. We will finally able to get the list of attributes of structure. And that's amazing, because only waited 30 years for that. And this is so stupid that it's not even funny. I mean, it's just a stupid thing. It's just the most trivial thing you want to do in analysis, in the most trivial case, that is this data structure. And we are getting this after 30 years. And in my opinion, a bad form for this, but that's another discussion. And I think there is no. Why I think there is no hope? Because every 3 years, the artificial complexity increases. So every new standard the language is more complex than the previous one, has more special cases. The syntax gets more complex. And this means that all the metacode that you wrote until today is broken. If you want to do, if the metacode was able enough to do some serious metaprocessing, right now it doesn't, so it doesn't really matter. But it's still a direction that is problematic. It started badly because C++ syntax was horrible from the beginning, horribly difficult from the beginning. And for many years, was a problem even to get compilers to agree on what was legal C++ and what was the semantic of a certain piece of code. And but it's getting worse every 3 years. So the complexity is increasing with every new version. And ad hoc solutions are added still today. So a new ad hoc thing that is compatible with the bad idea of just using quasi-quoting for the computation, that was a bad idea, with many structural problems. Instead of solving that structural problem, an ad hoc solution is added for a specific problem on that machinery. That is terrible. And so it's getting even more complex because of this. And every 3 years, this is what happens. And compile time session over the years is not kind of assessed correctly. There was, for example, we got a constexp, and that I don't think was a step in the right direction. I don't want to say that something is constexp. Everything should be constexp. I don't need a keyword constexp. In my opinion, constexp as a keyword doesn't make sense. Everything should be computable at compile time. And but I remember a kind of a movement after there was a talk, but there was a kind of this kind of feeling to it. There was context all the things, and I found that really stupid. I don't want the context keyword. That's how it should work. Not that I put context everywhere or allow context everywhere. I don't want to say context. But even worse than that, in a later after context was introduced, in a later version of the language, we also got consteval. And that means that there is a computation that you can only do at compile time. So reinforcing this idea that there are two distinct words, that they should not touch each other, they should not talk to each other, and one is the runtime, the other is compile time. In my opinion, this is a very bad distinction. It's all runtime. It's the use of code executing, so it's runtime. And before producing an executable, that's another aspect, but it's irrelevant. I want to be able to do any kind of computation at compile time. I remember when constexp was introduced, saying at a C++ conference, I was talking to some guru, or maybe some self-appointed guru, most probably, and I was talking about that I want a constexp open. I want to be able to open files, maybe open the network connection at compile time, because I, for example, want to read an XML definition, or I want to write an XML definition. I want to connect and ask for some, I don't know, some signature from a service, something like that, at compile time. And I still remember the eyes on their face, how I was looking at. Like I was, I don't know, crazy, singing, naked dancing, something like that, that they were close to call the police. Okay, and it is exaggerating, but not much. And for stating something that is should be, in my opinion, so obvious, why you don't want me to open a file at a compile time? I may need it. It's not your business. Of course, the open may fail. That's my problem. It's not your problem as a language designer. Once you want me to do computation, just let me do computations instead of anything. But this compile time session is reinforced each and every time. It's something that is not going to go away, in my opinion, given the current structure. And still, there is no code representation inside. There is this little attempt about the introspection for structures. I don't know exactly how much was defined to be there, but the function body is not even on the radar right now. So being able to do transformation metaprogramming or analysis metaprogramming, that has me, I don't know, if a certain function is trapping any exception. I want to check that at compile time. Maybe to tag that function for some logging, special logging, or something like that. And maybe wrapping, so I will get a log for every exception that comes there automatically without having to explicitly write a log line every time. And but this is just not possible, and it's not even on the dreams of the people that decide what C++ would be. And it doesn't matter if this is useful, doesn't matter if this would be a good idea. That's not how standardization work in these days. Standardization now is they decide that they know what is better for everyone, and they give you the perfect language. That's the idea, and in my opinion, a very bad idea. But this is the situation. And so that's why for me, C++ programming, there is no hope to get it fixed in any way. Okay. And the presentation is over. I am very open to get comments about any point of this presentation. Of course, if they're not just insults, that's I'm old enough, so I know all the bad words, so this is not going to help a lot. But if you think I'm wrong on any factual point, that would be very interesting for me. Or if you think that I'm oversight and I'm overly pessimistic, I would be happy to hear why. I'm old, so kind of being pessimistic is probably part of the game. I mean, it's part of getting old. So maybe there are nice parts that I'm missing, and I would really like to hear from you if you think the situation is not as bad I'm picturing it. Like I said, I'm not saying the C++ is bad. I mean, I'm saying C++ is bad, but I still think it's a very useful language. It's actually my language of choice for most low-level stuff I do. And other languages are much higher level. And but this is still my language choice, and it's also the language I use every day at work. And so I'm not against the C++ in general. I'm just saying that C++ metaprogramming sucks and is not getting better. There is no hope for fixing it. And actually, I don't use C++ metaprogramming a lot. I use it I use it to write C++ metaprogramming. Actually, I did more than I should have to. So now there are colleagues that are paying this 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 toll, this extra cost for my bad choice of going for metaprogramming stuff. So I wrote some needly complex library that is unfortunately now it's in use today. So it's a cost even removing it and replacing it with something saner. Maybe I will just spend time trying to do that. But that's it. So I'm not against C++. I'm just thinking that C++ metaprogramming sucks. And that's all. Thank you for watching and see you next time.